Alex chose positive integers a, b, c, d, e, f and completely multiplied out the polynomial product. After she simplified her result, she discarded any term involving x to any power larger than 6 and was astonished to see that what was left was 1 minus 2x. If a is greater than d plus e plus f, and b is greater than c plus d, and e is greater than c, what value of a did she choose? The first thing in this question is to try to simplify this, and we do that by noticing that there are certain algebraic identities that we can utilize. And these algebraic identities are used to simplify this into a slightly better form as follows. And I encourage you to go through these steps and figure out how we went from the initial given equation all the way to the bottom, which is right here. Basically, you take these algebraic identities and start subbing them in and then collecting like terms, and you will be able to get to this final step. This final step, the simplified version, is what we are going to work with, but we are going to make a few substitutions. This exponent we are going to call a, big A. So a will be a minus d minus e minus f. This exponent we are going to call b. So big B will be equal to b minus c minus d. And in a very similar way, that exponent we will call c, big C, will be e minus little c. And then big D we will call little d. And then just to be consistent, we will call the next one e, and the last one we will call f. Okay, so that means that this equation basically boils down to the following. It becomes 1 minus x to the a, 1 plus x to the b, 1 minus x cubed to the c, 1 minus x to the fourth to the d, 1 minus x to the fifth to the e, and finally 1 minus x to the sixth to the f. Okay? So at this point, we have to use binomial theorem to expand this. But the good news is that because we are initially going to be looking at values of x squared, because remember, this polynomial, when fully expanded, does not have anything of the form x squared, x3, x4, x5, or x6. So first, we are going to try to concentrate on the fact that there's no x squared when this whole thing is expanded out. So when we expand this using the binomial theorem, we initially only need to do it for the first two terms, because those two terms will give us an x squared, and all of these others won't. So that's why we only have to look at those first two. So first, let's talk a little bit about the binomial theorem. What is its general look? This is the general way that it would expand something using the binomial theorem. If it's 1 plus y, it would look like this. If it's 1 minus y, it would look like this. And the good news is that you only have to concentrate on the first few terms in order to get a x squared. So we will do that on this one right here. And there is our expansion. And we are only considering that we have to look at the x squared. So when you first did the expansion, it looks like this, right? But then when you simplify, it basically just boils down to this when you collect like terms. So the coefficient of x squared is just this guy right here. So that is what we will concentrate on. Now, since there is a term minus 2x and no x squared term in the full expansion, What that basically means is that this is equivalent to minus 2x. So minus a minus b x is equal to minus 2x. So that means a minus b must be equal to 2. And then this whole thing has got to be equal to 0 because there's no x squared term. So that means this, if you multiply it out, it becomes a squared minus a plus b squared minus b minus 2ab is equal to 0. I just multiply through by 2. If you factor this, you can do that. It becomes a minus b squared. And you can put the a and b on the other side. Now, a minus b is 2. So that means a plus b is equal to 2 squared, which is 4. So now I've got a minus b is equal to 2. A plus b is equal to 4. So I can add them. If I add them, I get 2a is equal to 6, and therefore a is 3. So that is my first letter that I have solved. And this one will quickly give me a value for b. B is going to be equal to 1. So I've got a and b so far. And in a very similar way, we're going to get the numerical values for C, D, E, and F. So now that we know a is 3 and b is 1, our polynomial now becomes 1 minus x cubed, 1 plus x to the power of 1. And then all the other ones we still don't know because we have not figured out those letters yet. But we can expand this out since we know these. And when you do, you get the following. 1 minus 2x plus 2x cubed minus x to the power of 4. And the rest remains the same. As we discussed before, we also have no x to the power of 3 in the full expansion. So that means that this x to the power of 3 must eventually cancel somewhere. And that minus 2x to the power of 3, that will cancel the positive 2x to the power of 3, that's got to come from this guy right here, because that's the only one that has x to the power of 3 in it. And therefore, we have to again use the binomial theorem to expand this, but we only have to do it in a way that we get the very first two terms. And if you do it, you will clearly see that the expression becomes 1 minus cx to the third. So that means this minus cx to the third has to be equal to minus 2x to the third in order for that to cancel with this guy, which appears right here. Because remember, the question says that when you do the full expansion, there is no x to the power of 3 term. So this basically means that c is equal to 2. So now we've got another one of those variables. Now, since c is equal to 2, that means my polynomial now becomes, and when you expand it, this is what the polynomial looks like at this point of our question. Now we continue in the very similar way. We have also been told that there's no x to the fourth, x to the fifth, and x to the sixth. And those are the ones that will help us solve for D, E, and F. So there is no x to the fourth in the full expansion, so we have to cancel this 3x to the fourth with a minus 3x to the fourth. And that minus 3x to the fourth has to come from 1 minus x to the fourth to the power of d, because that's the only term that has x to the fourth in it. So again, use the binomial theorem to expand this. And you only need to expand just so you get the first two terms, and that will easily show you that this must be equal to the minus 3x to the fourth. So minus dx to the fourth must be equal to minus 3x to the fourth, and therefore d is equal to 3. So now I have got another variable. So if d is equal to 3, my equation now becomes this right here, which I obtained by putting d equal to 3. Now at this point, again, we have to continue in the same way. We know that there is no x to the 5. So to cancel this 6x to the 5 that I have figured out, there has to be a minus 6x to the 5 that comes from here. And as before, we use the binomial theorem to expand this. And when you do, you get 1 minus ex to the 5th plus ... But we don't need to go any further. We just know that this has to be minus 6x to the 5. So that means minus ex to the 5 has got to be minus 6x to the 5, and therefore e is equal to 6. So I've got the second last one, and therefore as e is equal to 6, my expression now becomes equal to this. So at this point, we have just one letter remaining to solve. And by this point, hopefully you get the hang of this, that there's no x to the 6th. So this 9x to the 6th must be canceled by a negative 9x to the 6th. That's got to come from there. So, as always, with this question, we have to use the binomial theorem to expand. And when we do, we get 1 minus fx plus ... And then this, therefore, has to be 9x to the 6th. So minus fx to the 6th has to be equal to 9x to the 6th. Therefore, it had to be negative 9x to the 6th. That's what we need to cancel. So therefore, f is equal to 9. So there we go. We've gotten all the letters. And I will summarize all those letters. A we got as 3, B is 1, C is 2, D is 3, E is 6, and F is 9. Now recall, those were the big ones. We had made substitutions earlier. We had made the substitution that big A is equal to small a minus small d minus E minus F. That big B was equal to B minus C minus D. C was equal to small e minus small c. D was equal to just small d. E was equal to F, small f, and big F was equal to small c. So we can quickly get these. Some of these are pretty easy. C, therefore, is going to be equal to F, this small c, A, B, C, D, E, F, these small letters. C is equal to F, well, F is 9, so there we go. E is equal to F, so this small f is the same as big E. And then big D is equal to small d, so D is equal to 3. Now let's figure out E, B, and therefore A, where A is the one that the question is asking for. Well, from this equation right here, big C is equal to E minus C. Well, big C is 2. So 2 is equal to E minus C. And C, small c, is 9. So therefore, small e is 11. And then from this equation right here, our big A is equal to A minus D minus E minus F. Our big A is 3. A is what we're trying to figure out. Small d is 3. Small e is 11. Small f is 6. So therefore, A is equal to 3 plus 20. And therefore, A is 23. And that is the answer to the question. So number 25, the answer is E. What is the tens digit of 3 to the power of 2016? All right, so like all such questions, tens digit, units digit, you always try to look for a pattern. And the hope is that you get a pattern sooner rather than later. So let's write out our powers of 3. And let's see what the tens digit is and see if there's some sort of a pattern. All right, let's now write the tens digit beside each number. Well, this is 0. 0, 2, 8, 4, 2, 8. And remember, I'm just writing the tens digit here. 6, 8, 4. 4, 4, 2. 6, 0, 2. 6, 8, 6, 0. All right, do you see any pattern? And I don't. All right, so that means either two things. Either we have to keep going to find a pattern, or there is no pattern. If there is no pattern, then I'm not sure what to do here. Okay, let's keep going here. 3 to the power 21. So we got, let's see here, 0, 0, 2, 8, 4. 2, 8, 6, 8. 4, 4, 4. 2, 6, 0. And 2, 6, 8, 6, 0. 2, 6, 8, 6, 0. Okay, let's see here. And the good news is that we got a pattern. It's a 20 period pattern, if that's how you want to describe it. If you notice, once you get finished with 20, it starts repeating 0, 0, 2, 8, 4, just like here. All right, so that's pretty promising. We can figure this out now. So we want 3 to the power 2016. So it looks like every time we have a exponent that is a multiple of 20, the tens digit will be 0. Well, that's not a multiple of 20, but 2000 is. So if you had 3 to the power of 2000, that's a multiple of 20, and that units digit would be 0. So 3 to the power of 2001 would be the next guy, which is this. See what I mean? Then 3 to the power of 2002 would be the next units digit, which is this, which is 0. And then 3 to the power of 2003 would be the next units digit, which is 2, and so on. So when you count, we want to eventually get to 3 to the power of 2016. So let's just count. This was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 3 to the power of 2016 will have a units digit, that is 2. And that's it. So number 24, the answer is B. The product of n consecutive 4-digit positive integers is divisible by 2010 squared. What is the least possible value of n? So they're saying you've got some numbers, there's n of them, and they're all 4-digit numbers, and when you multiply them together, you've got this big long product, and it divides by 2010 squared. It gives you some integer. Okay, no problem. So that means that this number in the numerator has to include all of the prime factors of 2010 squared. So that is the first task of figuring out what is 2010 broken down into prime factors. It's 2 times 3 times 5 times 67. So if you have 2010 squared, it's basically 2 times 2 times 3 times 3 times 5 times 5 times 67 times 67. So this numerator up there has to include all of these guys. If it does, when you divide by 2010 squared, it will give you an integer. Okay, so let's figure this out. First and foremost, this is a very important point that they're 4-digit numbers. All the numbers that I put in my numerator, they have to be 4-digit numbers. So I have to first start off with creating a 4-digit number from these prime factors. And if you notice, these are very small numbers. Interestingly, even if you take all of them and you multiply them together, you actually still don't get a 4-digit number. You get 900. So the only way to get a 4-digit number that includes the prime factors is to involve the 67s. So obviously one such number would be 67 times 67. that's definitely going to be one such 4-digit number, and that number is 4489. Now, I think the challenging part of this question is that you can also create another 4-digit number as a reference point by including a 2. Because if you do 2 times 67 times 67, you will also get another 4-digit number that can be used, and that's 8978. You can't go any higher, because if you started using 3s and 267s, you would no longer have a 4-digit number. You'd have a 5-digit number. You'd have 13,000 something. So these are the only two 4-digit numbers. So my string of 4-digit numbers that I put in my enumerator has to be somewhere plus or minus those numbers. So first, let's just start with this guy here, and let's see what we get. All right, so we're going to start with 4489. Now, I don't know which direction we're going. Are we going greater or are we going less? So I'll just write in a few on either side. All right, now let's play this game here. My task is to involve all of these guys into a string of numbers that obviously includes 4489 as my sort of reference point. Well, let's see. Okay, so I've got to ensure that every single one of these prime factors is included in the numbers that I choose. So I'm starting with 4489. So 4489 is obviously divisible by 67. It was 67 divided by 67. 67 times 67. So that means this guy takes care of this guy and this guy. Okay? Now we can go in either direction. We can go this way or that way. It doesn't really matter. I'll just go this way, and then we'll see what happens. 4488. Well, that is obviously divisible by 2, and it's divisible by 2 once again. So it takes care of 2 2's. Now, can it be divisible by anything else? And the answer is yes. It can also be divisible by a 3. So this one helps us out quite a bit. 4487. Is that divisible by any of the remaining 3? 4487 is not divisible by 5, obviously, because it would have to end in a 5 or a 0. And it's also not divisible by 3. So that's a loser. How about 4486? Does that help me in any way? Is it divisible by 3? It's not. So that's a loser also. How about 4485? Is that divisible by 3? Yes. Is it divisible by 5? Yes. So this takes up that one and that one. Now, if I go in this direction, that's obviously divisible by 5 since it ends in a 0. So there you go. This string of 1, 2, 3, 4, 6 numbers, they're consecutive 4-digit positive integers, and when you multiply them all, they will all contain those factors which represent 2010 squared. So far, the answer looks like it could be 6. And in the answer choices, 6 is the second smallest. Oh, I see. So, it's possible that 5 could be the answer, so we got to keep going here, unfortunately. I was hoping that 6 was the smallest, but it's not. Okay, so let's go in this direction now. All right, we're going to obviously keep this 4489 because that takes care of 267s. Now let's go to 4490. 4490 obviously is divisible by 5, so that takes care of 1 5. And is it divisible by anything else? It is by 2. And then anything else? No, unfortunately. So far, we have those two. 4491, does that contribute or help us in any way? Is it divisible by 3? The answer is yes. So that takes care of 1 3. And it's divisible by 3 again. So I can circle another 3. 4492, obviously that's divisible by 2 since it's even. And I think that's it. And then we've got this one lone 5, and unfortunately I have to go all the way to include this guy, and this guy to get a number that's divisible by 5, which is this. So that would mean 1, 2, 3, 4, 5, 6, 7. Oh, now I got n equals 7. So that's worse, because they want the least possible. Okay, so this is the part of the question that I think is tricky. We have to now do the same story for this guy. And that being 8, 9, 7, 8. Okay, and same thing, we got to go in either direction. So 8, 9, 7, 8, this middle number, it was 67 times 67 times 2. So it takes care of those ones. Now let's go this direction. Doesn't really matter, but let's just go in that direction. Does that help us in any way? Is it divisible by 3? It's not. Is it divisible by 2? No. And is it divisible by 5? No. So that doesn't help us at all. How about 8, 9, 7, 6? It's obviously divisible by 2 since it's an even number. And then, is it divisible by 3? And the answer is yes. And anything else? No. So we got a couple of prime factors. How about 8, 9, 7, 5? That is obviously divisible by 5 because it ends in a 5. Then it's divisible by 5 again. And is it divisible by the final 3? No. But what about 8, 9, 7, 4? Is that divisible by 3? And the answer is no. Okay. Well, what if I go in this direction and try the 8, 9, 7, 9? Is that divisible by 3? And the answer is yes. So look at that. By using this guy, I got a string of only 5 numbers that include all the prime factors of 2010 squared. So the answer is n equals 5. So number 23, the answer is A. A positive integer is called a perfect power if it can be written in the form a to the power of b, where a and b are positive integers, and b is greater than or equal to 2. For example, 32 and 125 are perfect powers because 32 equals 2 to the power of 5, 125 equals 5 to the power of 3. The increasing sequence 2, 3, 5, 6, 7, 10, ... consists of all positive integers which are not perfect powers. The sum of the squares of the digits of the 1000th number in this sequence is not perfect powers. That is what this is. So what that basically means is that if you're going to write out all of these numbers, right, 1, 2, all the integers from 1 till some number, obviously, but let's just say 1 till 1,000. I'm not going to write them all out, don't worry. Until, let's say, 1,000. What we have to do is subtract from these, take away from this list, all the numbers that are perfect powers. And they've done that for the first few, right? They took away the 1, they took away the 4. What else did they take away here? They took away 8 and the 9, right? Because those numbers are perfect powers. And what they had left, 2, 3, 5, 6, 7, 10, they have put into this list. And we have to do the same. But we have to do it for the numbers all the way up till 1,000. But not to worry, it's not going to be as painful as you think. Because the good news is there's not as many perfect powers as you may think. You might think that there's like hundreds or whatever, right? There isn't. There's probably only going to be a few dozen. And that will take a little bit of time, but it's not too bad. All right, so let's just quickly make a list. 1 to the power of n. Any of those will be called a perfect power, as long as n is greater than 2. They're calling it b, I call it n, same thing. All right, well, what are those? Well, it's only going to be 1, right? Because 1 to the power of anything is 1. So that's easy. 2 to the power of n, what are those? When n is greater than or equal to 2, we got 4, 8, 16, 32, 64, 128, 256, 512, and 1024. I'm not going to go any higher than that because I think we just want to get up to 1,000, right? 3 to the power of n, let's see here. 9, 27, 81, 243, 729, and I think that's it. We don't need to go further than that, because if we do, it'll be much more greater than 1,000. 4 to the power of n, 16, 64, 256, 1024, and I'll stop there. 5 to the power of n. We got 25, 125, 625, and then I'll just stop at that point. 6 to the power of n, 36, 216. I don't need to go further than that, because that'll be quite a bit more than 1,000. 7 to the power of n, 49, 343. 8 to the power of n, 64, 512. 9 to the power of n, 81, 729. 10 to the power of n, 100, 1,000 exactly. And before I continue, let's keep a tally here of how many I got. For 1 to the power of n, I'll just do it on the side here. One number. For 2 to the power of n, how many did I get? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. I'm only going to use the ones less than 1,000. If I need it, if I need this guy later, I'll add it later. 1, 2, 3, 4, 5 for 3 to the power of n. 4 to the power of n. These ones I'm going to cross out because they are all included here, right? So you got to be careful about that. 5 to the power of n, I've got 3 unique ones. 6 to the power of n, 2. 7 to the power of n, 2. 8 to the power of n, they've already been counted, so I'm going to cross those out. 9 to the power of n, I've also been counted up here, so I got to cross those out. 10 to the power of n, I've got 2 unique ones. All right, so let's continue with this list. Now, at this point, what happens when you get to 11 and so on, that you're only going to have one number. Because if you keep going 11 to the power of, 3, it'll be far greater than 1,000. So I'll just make the list from 11 all the way up till what number? It's until I get to 1,000. So it's basically 31. So let me make the list and I'll come back. So here we go. This is our list here. And we got to cross out a couple of these that are doubles. 16 gives 256 when you square it, and that's already been counted up here somewhere like that. What else do we have doubles of? I think 25, this one, because that's going to be included here. Any others? 27, I think. 729 is already in here somewhere. Right here it was. And it's actually right there. And I think that's it in terms of doubles. So that's not actually that bad of a list. Let's make our tally here. These are all individuals. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I'll put an 18 here. All right, so what do we have in total? 1 plus 8, which is 9. 9 plus 5 is 14. 17, 19, 21, 23, and 18 gives me 41. I've got 41 numbers that are between 1 and 1,000 inclusive that I cannot use in this list right here, in this list, because we want only numbers that are not perfect powers. And what I just made, this big long list here, were perfect powers. All of these were perfect powers because they can all be written in the form a to the power of b. So from 1 to 1,000, 41 of them I gotta get rid of. So if I do that, I'm left with just 959 numbers, correct? Now I've got to get up to 1,000. Okay, no problem. That means that this list, ... has to go up another 41 to account for those numbers that I took out. So it's got to go up to 1,041, correct? Now, this is the part of the question that is not necessarily extremely difficult, but it's something that people would miss. And I made sure that I wrote it in there. 1024, don't forget about him. That is going to be somewhere in here, and that also has to be taken out. Why? Because it's a perfect power. It's in our list. So that means when you take that out, you got to go up by another number. So you got to go to the 1042nd number. Correct? And that will be the 1000th number in the sequence. All right? 1042. Now they want you to figure out, what do they want you to figure out? The sum of the squares of the digits. Okay? Our number is 1042. The sum of the squares of the digits. That would be 1 squared plus 0 squared plus 4 squared plus 2 squared. And that is 1 plus 16 plus 4, and that's 21. And therefore, the answer to number 24 is 21, and that would be choice E. In the diagram, there are 26 levels labeled A, B, C to Z. There is one dot on level A. Each of the levels B, D, F, H, J, and Z contain twice as many dots as the level immediately above. Each of the levels C, E, G, I, K, and Y contain the same number of dots as the level immediately above. How many dots does level Z contain? Well, we probably just have to write out the letters and then write out the numbers. It wouldn't take that long since it's only 26 letters of the alphabet. And we follow their system, which is partially shown. 1, 2, 2, 4, and that's all they show us. But they give us quite a bit of information in the question that each of the levels that are B, D, F, H, J, all the way to Z contain twice as many dots as the level immediately above. Okay? So the first few have already been given, so we just have to figure out the rest. So twice as many dots, right? So that means if this is 2 and this is 4, this will be 8, and this will be 16, and so on, right? So every second one it will double. So this is 32, 64, 128, 256, 512, 1024, 2048, 4096, and then it's 8192, right? And this is what they want us to figure out, Z, but just for the sake of completion, let's figure out all the other ones. The other ones, which are C, E, G, I, K, and so on, they contain the same number of dots as the level immediately above. So this would be 4, this would be 8, this would be 16, this would be 32, 64, 128, 256, 512, 1024, 2048, and 4096. So that really wasn't even necessary, but, just for the sake of completion. How many dots does level Z contain? Well, it's 8192. So number 21, the answer is D.